Bismillahirrahmanirrahim. Dear students, as we discussed in part 1 of this week's lecture, that in this week we are starting new method for the plotting of shear force and bending moment diagram, and we have already discussed the basic concept behind that new method, and we have discussed the relationships between load, shear and bending moments that we will be using to plot shear force and bending moment diagrams. So now we will solve a couple of problems, and we will see that how those relationships that we have derived can be used to directly draw shear force and bending moment diagrams without going into any cumbersome calculations and writing down a lot of equations for several different portions. So now we'll solve the problems, and I hope these solutions will help you in developing a very good concept about these relationships between load, shear and bending moment diagram and drawing these diagrams directly. So we will be in this week we will be solving some problems that we have already solved using the method of equations. We will solve them with the direct method, and then we will compare our solution with our current solution with our old solution, that whether we get exactly the same SFDs and BMDs or not. So let's start with our first problem. This problem is related to an overhanging beam that has a overhang on both the sides. So we have a hinge support here and a roller support on this side, and this extreme left end is subjected to a point load with a magnitude of 5 kilonewton, and then in this portion we have two loads acting. One is a point moment with a magnitude of 10 kilonewton meter, and a point load with a magnitude of 5 kilonewton, and there is another point load acting at the extreme right end of the beam whose magnitude is 10 kilonewton. And these distances, this left overhang is 3 meters long, this part is 2 meters, also 2 meters and 2 meters, and this is 3 meters. We can label these points A, B, C, D, E and F. This is a problem that we have already solved using the detailed method. And we have a hinge support here and a roller support here. It's a determinate problem. We'll have a vertical reaction here and we'll have a vertical reaction here. We may call this reaction as RB and this reaction as RE. Okay. Now first step in this method as well is the reaction calculation, and that reaction calculation is exactly the same the way we used to calculate it previously. Excuse me. So let's apply the conditions of equilibrium to calculate the reactions. Sigma Fy equal to 0 with the convention of upward forces as positive. 5 kilonewton force acting in the downward direction, so minus 5. RB is with positive sign acting in upward direction. Then we have this next is this moment, but as it is a moment and we are applying sigma Fy equal to 0, so this moment will not appear in the equation. And next is this 5 kilonewton force acting in downward direction, so with a negative sign, minus 5, and then this Re acting in upward direction, and then this 10 kilonewton force acting in downward direction, and this is equal to 0. If we rearrange this equation, we'll get Rb plus Re equal to 20, and we may call this equation as equation number 1. Now let's apply sigma ME equal to 0 with the convention of clockwise movement as positive. Alright, so about this point E, first of all, this 5 kilonewton force is producing movement in counterclockwise direction, so minus 5 and lever arm is 9, 3 plus 6. Then this RB, and RB will produce movement in clockwise direction, so with a positive sign, RB into 6. Then we have this movement 10 kilonewton meter, and it is acting in clockwise direction, so it will be positive. And as it is a movement by itself, it does not need to be multiplied with any lever arm. And next is this 5 kilonewton force, and it is producing movement in counterclockwise direction, so minus 5 and lever arm is 2. RE is passing through point E, so RE will not contribute in movement. And then this 10 kilonewton force, which is producing movement in clockwise direction, so positive 10 and the lever arm is 3. And this should be equal to 0. Now if we solve this equation, we get RB equal to 2.5 kilonewton. So we have calculated one reaction, and the other calculation and the other reaction from equation number 1. So RB is 2.5. If you plug in this value in equation number 1, plus RE is equal to 20. And this implies RE is equal to 17.5 kilonewton. So this completes our reaction calculation for this beam. Now in our regular method that we have studied till today, according to that method, our next step is to divide the beam into number of portions and then write down the equations for shear and bending moment. So it involves a lot of equation writing and then calculation of values, and then we go to the plotting of diagrams. But the beauty of direct method is that you don't have to do any one of those steps. You directly jump to the plotting of shear force and bending moment diagram, and you will use the concept that change in shear is equal to the area of load diagram and change in bending moment is equal to the area of shear force diagram. And also the magnitude of shear is equal to the slope of bending moment diagram, and the magnitude of load is equal to the slope of shear force diagram. These are the 4 relationships that we derived in this week's part 1 lecture, and we will be utilizing these relationships to directly draw the shear force and bending moment diagram. So we'll skip all those steps that involve equation writing, and we directly jump to the plotting of SFD and BMD. So let me draw the beam once again, and then we will plot the shear force diagram and bending moment diagram. So we have a beam with a hinge support here and a roller support here. Point load 5 kilonewton is acting here, and we have calculated this reaction RB, which is 2.5 kilonewton, and this reaction RE, which is equal to 17.5 kilonewton. We have a couple acting here, 10 kilonewton meter, and we have a point load acting at this point, 5 kilonewton. And what else do we have? We have a point load here, point load acting here, 10 kilonewton magnitude, and these distances are 3 meter. Let me label the beam first: A, B, C, D, E and F. If you remember, in this beam we had to consider like a lot of portions, 1, 2, 3, 4, 5. So if you go for the conventional method, by writing down the equations, we'll have to consider 5 different portions, and for each portion we'll have to write down the equation of shear as well as bending moment. 3, 2, this is 2 meters, and this is 2 meters, and this is 3 meters. Okay, so here is the beam. Now let me draw the guidelines to draw SFD and BMD. So we'll draw the guidelines at every location where we expect change in shear and bending moment. You guys are already familiar with this thing. Here we are. So now we have the guidelines. Now let's start drawing shear force diagram. Okay, this is 0, 0 line, and we are plotting SFD, and our units are kilonewton. Okay, so what we'll do, we will look at the applied loading, and then we will draw the shear force diagram. So at this point, I just realized that this alignment is not very good, but just this line is actually corresponding to point A. So at point A, what load is acting? 5 kilonewton load is acting in the downward direction at point A. So the value of shear corresponding to this point will be -5. We'll take this as -5. So this value is minus, and on the diagram you don't have to label plus or minus, because I think that will we don't need to do that. If any value is below 0, 0 line, it is understood to be negative. Okay, so -5 here. And then in this portion AB, is there any load acting in this portion AB? If there is no load acting in portion AB, then the shear force will remain constant for this portion. So the shear force diagram will go straight. It's also -5 here. Shear force is -5. And then at point B, what load is acting? Whether it's a externally applied load or a reaction, we'll treat both of them in exactly the same manner. 2.5 kilonewton load is acting in the upward direction. So from -5, we will add 2.5. -5 plus 2.5, we will reach at -2.5. Why we have moved in the upward direction? Because a force is acting in the upward direction with a magnitude of 2.5 kilonewton. So we reach here. Then from point B to C, is there any load acting? No, there is no load acting from B to C, so the shear force diagram will remain constant, 2.5. And what about C to D? This is a movement, and the effect of movement does not reflect in shear force diagram. So this value of shear force diagram will remain constant at this point. There will be no variation here. And from C to D, again there is no variation. It will remain constant. And then at point D, what do we have? There is a point load acting in the downward direction with a magnitude of 5. So -2.5 minus 5, that will bring us to -7.5. So we reach here 7.5. And then from point -7.5, from point D to point E, is there any externally applied load? No, there is no applied load. So in this region, the value of shear force will remain constant. And then at this point, we have a point load or reaction acting in the upward direction with a magnitude of 17.5. So -7.5 plus 17.5, and this will bring us to +10. So this ordinate is plus 10. How did we reach here? Minus 7.5 plus 17.5. And then from point E to F, is there any load acting from E to F? There is no load acting from E to F, so shear force will remain constant. This is 10. And then at point F, we have a point load with a magnitude of 10 kilonewton acting in the downward direction. And when we move in the downward direction equal to 10, we reach at 0, which means that our shear force diagram is closed. And this thing we already know, that our shear force diagram and bending moment diagram are correct if they close. So this shear force diagram is closing, which reflects that this diagram is correct. Positive, and this part is negative. When we will complete this problem, I will show you our previous solution as well, the diagrams that we plotted using the method of equation, and we will see that whether we have got exactly the same diagram or not. So this completes shear force diagram. Now let's move to bending moment diagram. BMD, and our units will be kilonewton meter. Okay, what is the relationship between BMD and SFD? The area of SFD is equal to the change in bending moment, and the slope of bending moment diagram is equal to the magnitude of shear force diagram. So we will use these two relationships in order to draw bending moment diagram directly. At point A, is there any point movement acting at point A? It's free end and no point movement is acting, so the value of bending moment will be equal to 0. We'll start from this point. And then from point A to B, how much is the area of shear force diagram? Because this area of shear force diagram is equal to the change in bending moment that will take place while moving from point A to point B. Just to make it clear, when we draw SFD, we look at the applied loads, and when we draw BMD, we look at the SFD. So how much is this area? 5 into 3. This horizontal dimension is 3 and the vertical dimension is 5, right? So 3 into 5, 15. It means the value of bending moment at this point, at point B, is 15. And the degree of shear force diagram is 0, so the degree of bending moment diagram will be 1. The degree of bending moment diagram is always one level higher as compared to the degree of shear force diagram. So 0 degree line, we will join these points with a straight inclined line or a first degree line, and the value here is 15. Okay, and then from point B to point C, how much is the area of shear force diagram? The current value of bending moment is minus 15, and the area of this shear force diagram is 2.5 into how much? Into 2. So if we want to calculate the value of bending moment here, if I just write it down for clarity on this side, when you will be solving it, you don't have to write it down, but I'm just writing it down for clarity. So current value of bending moment is minus 15, and how much is the value of area in this region? That is, the one thing is that we need to incorporate the sign as well, so it's minus, and the area is 2.5 into 2. Minus 15 minus 2.5 into 2, if you solve this, you get minus 20. Minus 20 kilonewton meter. So it means that the value of bending moment at this point is minus 20. And again, the degree of this line, this is 0 degree line, so these 2 points will be connected with a first degree line. And then at this point, one thing that we need to be careful about, that at every point we need to make sure that if a point moment is acting, that point, the effect of that point moment will not reflect in the in the shear force diagram. For that, we will have to consider the applied loading. For example, there is no hint from the shear force diagram that a point moment is acting at point C. For that, we need to keep an eye on the applied loading as well. So at point C, there is a point moment acting, and how much is the magnitude and direction of this moment? It is 10 kilonewton meter acting in the clockwise direction, and according to our convention, clockwise movement is positive. So we will take it as positive, and we are at negative 20. So the second value at the same point will be minus 20 plus 10 equal to minus 10. So the second value of bending moment at the same point is minus 10. We can label it somewhere over here. Okay. And then at this point, when we want to move to point D, we will have to consider the area between C and D of SFD to get the value here. Currently at point C, the value is minus 10. And how much is this area? This area is also negative, and this is minus 2.5 into 2, which makes minus 15. Okay, so we are at minus 15. And again, SFD is 0 degree, so BMD will be first degree. This is minus 15. And then at point D, is there any point moment acting? No, there is no point moment acting. So it will have only single value. And then from moving from D to E, how much is this area? If I write it down here, the current value is minus 15. Okay, and this area is negative 7.5 into 2. So minus 15 minus 7.5 into, sorry, this is not 12, this is 2. Okay, and it gives us minus 30. Okay, minus 30. So minus 30 would be somewhere over here. And how to connect these 2 points? This is 0 degree line, so the bending moment diagram should be first degree line. First degree line here. We reach at minus 30. And then from minus 30, we need to see how much is the value here. How much is this area? Positive area. If I write it down here, we are currently at minus 30, and the area of SFD is positive 10 into 3. And this brings us to 0. Right? And how to connect these 2 points? SFD is 0 degree, so BMD will be first degree. So we will connect these 2 points with a first degree line, and our bending moment diagram is closing at this point. That once again means that bending moment diagram is correct. So the entire bending moment diagram is negative here. So this completes our bending moment diagram using the direct method, and you guys would have surely noticed that this method is a lot easier and simpler as compared to the laborious method of equation. Now let me compare this solution with our old solution. Here, this is our old solution that we did earlier. It's exactly the same problem. We determined the reactions, and then we wrote down the equations, and we had a lot of segments, portion A, B, B, C, C, D, D, E, and portion E, F. So we did a lot of calculations, and after that we drew these diagrams. Now these are the diagrams that we made earlier using the detail method, and you can see that these diagrams are exactly the same as that we have obtained today. Let me see if I can put them together in a single view. Oh, I think my camera cannot accommodate that, but this is the old solution, this one, and here is our new solution, and both are exactly the same. So you can see that if we follow the relationship between load, shear and moment, then easily we can end up with the same shear force and bending moment diagrams. In this problem, we learned how to deal with point load and point moments, and using this method we will solve a lot of problems, and we will also learn how to deal with UDLs and VDLs, and when we have a moment or a point load acting in combination with a UDL or a VDL. So we will learn all those things. So with this problem is completed. I hope it is clear. So thank you very much. Let me stop recording here.